Hey everyone, and welcome back as we open up our discussion of the properties of the normal distribution. Taking a look at our first objective, we need to use the uniform probability distribution. So we're not talking about the normal distribution yet, but instead first, the uniform distribution is a distribution in which all intervals of the same length are equally likely to occur. It's a little bit of a loose comparison, but the uniform distribution kind of connects to our equally likely probabilities in terms of our probability discussion. Like rolling a fair die, where each outcome is equally likely to occur, it's the same idea here, but in terms of a distribution. We'll elaborate on that though, with some examples. The next idea though would be a probability distribution function. This is an equation used to compute probabilities of continuous random variables. They must satisfy the following two properties. First, the total area under the graph of the equation must equal 1, and then the height of the graph must be greater than or equal to 0 for all possible values of the random variable. The height of the graph will represent the probability of the outcome in discussion. But let's go ahead and jump into the first example here to help us elaborate on that. Now this example is going to look a bit lengthier than it needs to. I'll try to keep it a little concise in the explanation though. Within the example though, we're explaining step by step why this is the uniform distribution. So first, suppose the United Parcel Service, UPS, is supposed to deliver a package to your front door and their arrival time is somewhere between 10 a.m. and 11 a.m. Here's the part where it gets a little iffy with the language. Let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. The delivery could be at 10 a.m., which would be x equal to 0, or at 11 a.m., where x is equal to 60, meaning 60 minutes after that 10 a.m. with all 1 minute intervals of times between x equals 0 and 60 equally likely to occur. Now this is the key aspect. Since each 1 minute interval is equally likely to occur, that allows us to recognize that we have a uniform distribution. So that's our first layer. We know that we have a uniform distribution that we're working with. First, the graph illustrates the properties for the example we're discussing. Notice the area of the rectangle is 1 and the graph is greater than or equal to 0 for all values of x between 0 and 60 inclusive. That is, the area of our rectangle in here is 1, but this goes back to our knowledge of area of a rectangle. If you don't remember, area of a rectangle would be length times width. It doesn't matter which one we call the length or the width. If we call our x-axis the width, then that means our length would be our vertical values. And that means we've got a 1 over 60 being multiplied by our width, that would be a 60. Of course, that leads to our 1, hence the area being 1, just for a little review in case that helps. That also explains why the height must be 1 over 60 in order for the area to be 1. Now this comes into play later. The way that problems will be presented is we'll have an interval of the x-axis, like we do in this example, where x is between 0 and 60. Well, if we have that, we can use our x-axis and the interval that is available to determine what the height of our graph needs to be. Right now, values of the random variable x less than 0 or greater than 60 are impossible. Thus, the function must be 0 for x less than 0 or greater than 60, like we see in the graph here. The reason why they're impossible is we're told that our package will not be delivered before 10 a.m. or after 11 a.m. Thus, there's a 1 hour window here, and they've guaranteed us that the package will be delivered in that 1 hour. So it shouldn't come before that or after. But here's the big new concept that we're trying to grasp through this example. Not just that we're working with a uniform distribution for the first time, but that the area under the graph of a density function. A density function is what we just showed with those graphs. But the area under the graph of any density function over an interval represents the probability of observing a value of that random variable in that interval. To de-staticify this a little bit, the new concept is the area under the graph represents probability for us. So now we want to think of this as, if we're trying to find probability, that means we just need to find the area under the graph. Let's head into our follow-up example then to elaborate a little bit more. Simplifying this a little bit, it gets a little more straight to the point. What is the probability that UPS delivers the package between 10:15 and 10:30 inclusive? That is, we're trying to find the probability that our delivery time is between 15 and 30 minutes after the hour, and we know that's represented by the area under the graph. Well, in order to find the area under the graph, we first make this rectangle within our rectangle. Since our interval is between 15 and 30, those are the x values corresponding to our interval. We're trying to find the area between those two marks. Well, we know one more time that area is length times width. One more time, if we call the length our 1 over 60, that means we get to substitute that into our formula. And now the width, rather than being 60, would just be our 30 minus 15. Of course, that would be 15. So as we substitute that into our area formula, we can simplify that up a little bit. Not to make you bust out your fraction skills, but we get an area of 1 over 4. And that means the probability that we have a delivery time between 15 and 30 minutes would be a 0.25. And we're all set finding our probability, which one more time was represented by the area under our graph. But the area we were finding was the rectangle within our graph between the values of 15 and 30. And that's how we handle the uniform probability distribution. Heading over to number 2, just to make sure we're comfortable. Now they're asking us, what is the probability that UPS delivers the package between 10:50 and 11 a.m.? Now we know 11 a.m. represents the value where x is equal to 60, because that would be 60 minutes after our starting time of 10 a.m. And 10:50 would be x equal to our 50 minutes after our starting time of 10 a.m. We see that rectangle drawn on the graph, and again we just need to find the area of our rectangle. And we know our area one more time would be length times width, our length being our 1 over 60, or the height of our graph. And this time the width, 60 minus 50, would just be 10. So we end up with an area of 1 over 6, and that means our probability that x, the delivery time, is between 50 and 60 inclusive, is approximately 0.1667. Again, the key idea being the probability is represented by the area. And that means we're all set finding probabilities using the uniform probability distribution. Well, that takes us to our next objective then, which would be the graph of a normal curve. We're just discussing now the properties of our normal curve. Hopefully this feels familiar, meaning we have a bell-shaped distribution. Jumping into the properties, relative frequency histograms that are symmetric and bell-shaped are said to have the shape of a normal curve. You'll hear us using the term normal curve or normal distribution a lot more now as opposed to just bell-shaped. It's the specific type of distribution that we'll be working with quite a bit. If a continuous random variable is normally distributed or has a normal probability distribution, then a relative frequency histogram of the random variable has the shape of a normal curve, which we just said is bell-shaped and symmetric. This also means that the empirical rule can be applied. And again, that's a big deal because as soon as we recognize we have a normal curve, which we know would be bell-shaped and symmetric, like we've had before when we work with the empirical rule, that means we're right back into what hopefully is a comfortable situation with that idea of the empirical rule. Continuing then to our next objective, we want to state the properties of the normal curve. That is, we're getting a little more detailed now. Remember with the empirical rule, that was an approximation. We see this graph here that has a lot of information presented to us. It's simply the breakdown of our empirical rule. Well, looking at these properties, our normal density curve here, or the normal curve, is symmetric about its mean mu. That is, we notice that the mean is in the center, just like when we used our empirical rule. Because the mean, median, and mode are all the same, the curve has a single peak, and the highest point occurs at x equal to mu. It has inflection points at mu minus sigma and mu plus sigma. It's not a huge emphasis, but it's just where the graph starts to change concavity. We're just planting that seed, though, in terms of the math that's behind the scenes. Not something huge for us to worry about, though. As discussed with a uniform distribution, the area under the curve here is still 1. Remember, that's the total area under this whole curve. The area under the curve to the right of mu is equal to the area under the curve to the left of mu. That's because, again, our graph is symmetric about the mean. Next, a little bit of a calculus topic going on here, but not a huge stress. As x increases to infinity or decreases to negative infinity, the graph approaches, but doesn't technically reach the horizontal axis. And one more time, we've previously stated that the empirical rule applies. Again, those are all our properties, explaining what we have to work with when dealing with this normal distribution, but we're concerned with how we apply them, and we'll explain that with some examples. And that takes us right into our next objective, where we need to explain the role of area in the normal density function. Well, the area under the normal curve has to do with a random variable x that is normally distributed with a mean mu and a standard deviation sigma. And if we have this situation, the area under the normal curve for any interval of values of that random variable x represents either the proportion of the population with the characteristic that we're describing, or the probability that a randomly selected individual from our population will have the characteristic that's under discussion as well. Now this is a big deal to us. Again, to de-statify this thing, what we're saying is the area under the normal curve represents either the proportion or the probability of whatever is under discussion. But we'll jump into our example to explain this further. Taking a look at our example then, we're told the weights of giraffes are approximately normally distributed, and we're going to pause there, as we'll see this quite a bit, but this is a huge deal for us to recognize that we're working with the normal distribution. As soon as we see that we're working with the normal distribution, we want to be thinking that normal curve, and that sends us down the right path in terms of finding whatever it is we end up being asked. Back to the question then. We have a normal distribution. They give us the mean of 2,200 pounds and the standard deviation is 200 pounds. We need to draw a normal curve with the parameters that they gave us, and then we want to shade the area under the normal curve to the left of the value of x being 2,100 pounds. Well, one more time, that means the first thing we're doing is drawing that normal curve, since we have a distribution that is approximately normal. Now that we have our generic normal curve, we can start throwing in the details for this particular example. That is, first they give us the mean of 2,200 pounds, and since we have a sigma of 200 pounds, mu minus sigma would be 2,000, and mu plus sigma would be 2,400. We need to shade the area of the normal curve to the left of the x value, being 2,100 pounds, so that means our x value would be between our mean and 1 sigma below the mean, and shading the area to the left means we have our graph of the normal distribution with these given parameters. Now if that's okay, let's go ahead and jump down to part B of the question. We're using the graph that we just drew, and we're told suppose that the area under the normal curve to the left of that 2,100 pounds, which is the area that we shaded in purple here, and they're saying that area is a 0.3085. We need to provide two interpretations of this result. Well again, the shaded area, we're told, is 0.3085. And now this just goes back to that definition as previously discussed. The two interpretations would be the proportion of giraffes, since that's what we're talking about, whose weight is less than 2,100 pounds, is 0.3085, the value that they gave us. Or we can think of this area that we have shaded as the probability that a randomly selected giraffe weighs less than 2,100 pounds is that same figure, a 0.3085. One more time, the idea being, which is a huge idea, the area that we have shaded in our graph represents either the proportion of all giraffes or the probability that a randomly selected giraffe weighs less than 2,100 pounds. And that's the big concept that we're trying to connect and really keep at the forefront of our minds as we move forward. The area under the graph represents either proportion or probability. And that wraps up our conversation on the properties of the normal distribution. And thank you for joining us one more time.